Okay, let us continue the second part of today's class. Okay, we have mentioned the equation 3.4. Okay, let us review the last part. Okay, equation 3.4. Okay, in equation 3.4, the expectation of square of the absolute value of zi is defined as sigma square, which is equal to 1. Okay, let us go back to page 15 and equation 3.5. Okay, in equation 3.5, the expectation of the square of the absolute value of Si is defined as sigma S squared, which is equal to 1 over Nt. Okay. The capacity of the MIMO channel can be rewritten as follows. Okay. The capacity C is equal to log 2 of the determinant INR plus. Okay, you can compare equation 3.7. Okay, and here 3.8. Okay, you can find that because sigma square is equal to 1. Okay, let us see. Sigma square is equal to 1. And sigma S square is equal to 1 over Nt. Okay, sigma S square is equal to 1 over Nt. So this term is equal to 1 over Nt. Okay, and because H is equal to the square root of rho times H prime. Okay, so for two H times H Hermitian together, we will have a term rho, and H becomes H prime Hermitian. The expression for the MIMO capacity in this equation is found in many references on MIMO communications. It is important to keep in mind, however, that this expression only applies under the assumptions delineated. Okay, what is the meaning of this word? Let us see the handout. Okay, page 16. Problem 1. What is delineate? Solution: to describe or mark the age of something. Okay. So let us go back to the slides. Okay, delineated or described in this section, which are only optima under CSIR only conditions. Equation 3.8. Okay, let us go to equation 3.8. Okay, is this equation. Okay, this equation does contain an explicit term for the signal to noise ratio, that is rho, and the channel matrix is normalized. This allows us to drop the prime and write equation 3.8 in the following form. Okay, let us see equation 3.8 again. We drop this prime and drop this prime. That is, we remove these two primes. And finally, we will get this equation. Okay, C is equal to log 2 of the determinant of INR, okay, where INR is an NR by NR identity matrix, plus rho over NT times H Hermitian. Okay, next let us go to section 3.2, eigenchannels and channel rank. Okay, when you see the word eigen, okay, or the prefix eigen, I think you can know that it is related to eigenvalues and eigenvectors, which you have learned in the course linear algebra. We start by considering matrix theorem, section 1.9.2u. Okay, let us go to section 1.9.2u. Okay, this. And we search for u. Okay. Okay, this is section 1.9.2u, eigenvalue decomposition. Suppose that A is a Hermitian matrix of dimension m by m and rank R. It follows that there is an m by m diagonal matrix D, okay, and with dimension m by m, which is equal to a diagonal matrix, and its diagonal elements are lambda 1, lambda 2 to lambda r, 0 to 0. Okay, the number of zeros here is equal to m minus r, and a normalized unitary matrix U dimensioned m by m such that A is equal to U times D times U Hermitian, where lambda I are the eigenvalues of A and R is equal to R of A, that is the rank of matrix A. In this case, the columns of U, okay, the columns of U, this matrix, are the eigenvectors associated with the eigenvalues in D. Okay, let us go back to chapter 3. Okay, let me change the pointer. Okay, which states that any Hermitian matrix can be expressed as a product of three matrices in an eigen decomposition. Okay, since H times H Hermitian in equation 3.9, okay, let us go to equation 3.9. Okay. Okay, in equation 3.9, here is there is a matrix H times H Hermitian. Okay, let us go back to here. Okay, it's Hermitian. Okay, why this matrix is Hermitian? Let us see the handout. Okay. Page 19. Problem 1. H times H Hermitian in equation 3.9 is Hermitian. Why? Okay, next page. A solution. H times H Hermitian and Hermitian again is equal to H Hermitian times H Hermitian, which is equal to H times H Hermitian, where the first equality, okay, this equality results from section 1.9.2c. Okay, let us see the slides of chapter 1 and go to 1.9.2.c. Okay, for any matrices A and B, A times B Hermitian is equal to B Hermitian times A Hermitian. Okay, please note that you must exchange the order of B and A. Here is A times B, and here is B Hermitian times A Hermitian. Okay, let us go back to the handout. Okay, so this equality results from the section 1.9.2c. Therefore, H times H Hermitian is Hermitian. Okay, you can see that its solution is just as the same as the solution of homework 1. Okay, let us go back to the slides. It follows that we can decompose it as follows. H times H Hermitian is equal to UNR. Okay, UNR means this matrix U is an NR by NR matrix times DNR times UNR Hermitian. Okay, where D is a diagonal matrix and its diagonal elements are lambda 1, lambda 2 to lambda r and some zeros, and the number of zeros here is equal to NR minus R, and R is equal to R of H is equal to R of H times R H Hermitian. Okay, why the rank of H is equal to the rank of H times H Hermitian? Okay, let us see the handout. Okay, page 20, problem 1. Prove that R of H is equal to R of H times H Hermitian, where R denotes the rank of a matrix. Solution, it is left to you as an exercise. Okay, because I believe that you have taken the course linear algebra when you are freshmen, and if you have taken this course, you should be able to solve this problem. Okay, and the subscripts explicitly indicate the dimensions of the square matrices in the decomposition. Okay, the subscripts is NR, NR, NR. Okay, it means that U, D, and U Hermitian are all NR by NR matrices. Okay, plugging equation 3.10 into equation 3.9 yields. Okay, let us go to equation 3.10. Okay, H times H Hermitian is equal to U du Hermitian. And let us see equation 3.9. Okay, in equation 3.9, C is equal to log 2 of the determinant of INR plus rho over NT times H Hermitian. Okay, so yields C is equal to log 2 of the determinant of I plus rho over NT times U du Hermitian. And this equation can be rewritten as this equation, which is equal to log 2 of the determinant of U times I plus rho over NT times D times U Hermitian. Okay. why does this equality hold? Okay, please see the handout. Okay, page 21, problem 1. How does one get the second line of equation 3.11? Solution. Because U is a unitary matrix, U times U Hermitian is equal to I. And because I is the identity matrix, U is equal to U times I. Plugging equation 3 into equation 2. Okay, this is equation 3 and into equation 2 yields UIU Hermitian is equal to I. Okay, therefore the right hand side of the first line of equation 3.11 becomes. Okay, let us see the right hand side of the first line of equation 3.11. Okay, is this equation. Okay, becomes log 2 of the determinant of I plus rho over nt times u du Hermitian, and I, according to equation 4, is equal to uiu Hermitian. And observe these two terms. We can see that they have two common terms. Okay, first is the u, so we can take u here, and the second common term is u Hermitian, so we can put u Hermitian here, and the remaining terms are I plus rho over nt times d. Okay, so here is I plus rho over nt times d. Okay, let us go back to the slides. Okay, and this is equal to the log 2 of determinant of u times determinant of I plus rho over nt times d times determinant of u Hermitian. Okay, why? Okay, let us go to here. Okay, where the third step follows from matrix theorem, section 1.9.2L. Okay, let us see section 1.2.9L. Okay, for any square matrices A and B, it follows that determinant of A times B is equal to determinant of A times determinant of B. Okay, if there are three matrices, the result is the same. Okay, determinant of A times B times C is equal to determinant of A times determinant of B times determinant of C. Okay, let us go back to chapter 3. Okay, 1.9.2L. Okay, so we have the determinant of this, of the product of these three matrices is equal to the product of the determinant of each matrices. And then this equation is equal to log 2 of the determinant of I plus rho over nt times d. Okay, why? Okay, because we can go to page 23. Okay, and step 4 follows from matrix theorem, section 1.9.2J. Okay, let us go to section 1.9.2J. Okay, IJK. Okay, for any normalized unitary matrix U, the determinant of u is equal to 1. Okay. So we can know that the determinant of u is equal to 1. But why does this term also equal to 1? Okay, why does the determinant of u Hermitian also equal to 1? Okay, it is left you as an exercise because I think it is very easy to solve. Okay, then this equation is equal to log 2 of the product from I is equal to 1 to r. 1 plus rho over nt times lambda I. Okay, why does this equality hold? Okay, let us see the handout. Okay, page 22, problem 1. Derive the fourth line of equation 3.11. Okay, solution, it is left to you as an exercise. Okay, as I have told you before. Okay, problem 2, how do you get the fifth line of equation 3.11? Okay, solution. Because D is a diagonal matrix with diagonal elements lambda 1, lambda 2 to lambda r, and some zeros. The number of zeros here is equal to nr minus r. Okay, we can immediately have, okay, I plus rho over nt times d is also a diagonal matrix with diagonal elements 1 plus rho over nt times lambda 1, 1 plus rho over nt times lambda 2, dots 1 plus rho over nt lambda r. Okay, and 1 dots 1. Okay, the number of ones here is equal to nr minus r. Okay, I think it is very easy to see this. Okay, if you do not know why does this equality hold, okay, you can ask me. Okay, therefore the log 2 of the determinant of I plus rho over nt times d is equal to log 2 of the determinant of this diagonal matrix. And it is easy to know that the determinant of a diagonal matrix is equal to the product of the diagonal elements of the diagonal matrix. Okay, I think it is easy to prove it. So I do not want to go through too many details here. So this is equal to log 2 of the product from I is equal to 1 to r, and 1 plus rho over nt times lambda I. Okay, this completes the solution. Okay, finally, we can use a property of the log function. Log 2 of the products of some numbers is equal to log 2 of each number, and then sum them together. Add them together. So this equation is equal to summation I is equal to 1 to r. Log 2 of 1 plus rho over nt times lambda I. Okay, we have talked about this. The third step and the fourth step, okay, comes from two matrix theorems in section 1.9.2. That is, Okay, it is 25 minutes. Let us take a break.